Welcome. Today we're diving into the fascinating world of machine learning, focusing on two of its most fundamental approaches, supervised and unsupervised learning. Whether you're new to the field or looking to refresh your understanding, this video will break down the key differences, practical examples, and real-world applications of both methods. Let's start by setting the stage for what machine learning is, and why these two approaches are so important in shaping how computers learn from data. Supervised learning is like teaching a child with flashcards. You provide the computer with input data and the correct answers, known as labels. The model learns by comparing its predictions to the actual answers and adjusting itself to improve accuracy. This approach is widely used for tasks like image recognition, spam detection, and predicting house prices. The key idea is that the model learns from labeled data, making it powerful for situations where you know the outcome you want to predict. Supervised learning, on the other hand, is like exploring a new city without a map. Here, the computer is given data without any labels or correct answers. The goal is to find patterns, groupings, or structures within the data. This method is commonly used for clustering customers by behavior, detecting anomalies, or reducing data complexity. Unsupervised learning helps uncover hidden insights when you don't have predefined categories or outcomes. Most significant difference between supervised and unsupervised learning is the presence of labels. In supervised learning, every piece of data comes with a label, guiding the model's learning process. In unsupervised learning, there are no labels, so the model must find structure on its own. This fundamental distinction shapes how each approach is used and what problems they can solve. Let's look at some real-world examples of supervised learning. Imagine a spam filter that learns to distinguish between spam and legitimate emails by being trained on thousands of labeled messages. Or consider a medical diagnosis system that predicts diseases based on patient data and known outcomes. These systems rely on historical data with clear labels to make accurate predictions in the future. Supervised learning shines when you need to find patterns without prior knowledge. For instance, businesses use clustering algorithms to segment customers based on purchasing behavior, helping tailor marketing strategies. Another example is anomaly detection, where unusual patterns in network traffic might indicate a security threat. These applications show how unsupervised learning can reveal valuable insights from unstructured data. Supervised learning, the process starts with a dataset containing both inputs and their corresponding labels. The model is trained by feeding it these examples, allowing it to learn the relationship between the inputs and outputs. Over time, the model adjusts its internal parameters to minimize errors. Once trained, it can predict labels for new, unseen data with impressive accuracy. Unsupervised learning begins with a dataset that lacks labels. The model analyzes the data, searching for similarities, differences, or underlying structures. Techniques like clustering group similar data points together, while dimensionality reduction simplifies complex datasets. The model's goal is to organize and interpret the data, often revealing patterns that weren't obvious before. Training data is the backbone of supervised learning. Each example in the dataset includes both the input features and the correct output label. The model uses this information to learn how to map inputs to outputs. The quality and quantity of labeled data directly impact the model's performance, making data preparation a crucial step in the process. In unsupervised learning, the data consists only of input features with no labels or outcomes provided. The model must make sense of the data on its own, often by grouping similar items or identifying unusual patterns. This approach is especially useful when you don't have labeled data or when you want to explore the data's natural structure. One of the most common tasks in supervised learning is classification. Here, the model learns to assign inputs to predefined categories. For example, an email classifier might label messages as spam or not spam. The model is trained on labeled examples and then predicts the category for new data based on what it has learned. Clustering is a key technique in unsupervised learning. The model groups similar data points together based on their features without any prior labels. This is useful for customer segmentation, organizing large datasets, or discovering natural groupings in data. Clustering helps make sense of complex information by highlighting similarities and differences. Another important supervised learning task is regression. Here, the model predicts a continuous value such as house prices or temperature. The model is trained on labeled data, learning the relationship between input features and the target value. Regression is widely used in finance, real estate, and many other fields where predicting numbers is essential. Dimensionality reduction is a powerful unsupervised learning technique. It simplifies complex datasets by reducing the number of features while preserving important information. This makes it easier to visualize data, speed up processing, and improve model performance. Techniques like PCA, principal component analysis, are commonly used for this purpose. Workflow for supervised learning typically involves collecting labeled data, splitting it into training and testing sets, training the model, and evaluating its performance. This structured process ensures that the model learns effectively and can generalize to new data. Each step is crucial for building reliable and accurate predictive models. In unsupervised learning, the workflow starts with gathering unlabeled data. The model then analyzes the data to find patterns or groupings. There's often an exploratory phase where you interpret the results and decide how to use the discovered patterns. This flexible process is ideal for uncovering insights in complex or unknown datasets. Evaluating a supervised learning model involves measuring how accurately it predicts labels on new, unseen data. Common metrics include accuracy, precision, recall, and mean squared error. These metrics help you understand the model's strengths and weaknesses, guiding further improvements and ensuring reliable performance. Evaluating unsupervised learning models is more challenging because there are no labels to compare against. Instead, you might use metrics like silhouette score for clustering or visual inspection of the results. The focus is on how well the model finds meaningful patterns or groups within the data. Supervised learning offers several advantages. It provides clear guidance for the model, often resulting in high accuracy when enough labeled data is available. The approach is well suited for tasks where the desired outcome is known, making it ideal for classification and regression problems. Its structured nature also makes evaluation straightforward. Unsupervised learning excels when you have lots of data but no labels. It can reveal hidden patterns, groupings, or anomalies that might not be obvious. This makes it valuable for exploratory analysis, data organization, and discovering new insights in complex datasets. Despite its strengths, supervised learning has limitations. It requires large amounts of labeled data, which can be expensive and time-consuming to obtain. The model's performance is also limited by the quality of the labels. If the data is mislabeled or incomplete, the model may learn incorrect patterns. Unsupervised learning also has its challenges. Without labels, it can be difficult to evaluate the quality of the results. The patterns found may not always be meaningful or useful, and interpreting the output often requires domain expertise. Despite these challenges, it remains a powerful tool for data exploration. Supervised learning is best used when you have a clear outcome to predict and access to labeled data. It's ideal for applications like fraud detection, medical diagnosis, and sentiment analysis, where accuracy and reliability are critical. If you know what you want to predict, supervised learning is often the way to go. Unsupervised learning is the method of choice when you want to explore data, find hidden patterns, or organize information without predefined categories. It's especially useful for market segmentation, anomaly detection, and data visualization. When you don't know exactly what you're looking for, unsupervised learning can help you discover new insights. Common supervised learning algorithms include decision trees, support vector machines, and neural networks. Each has its strengths and is suited to different types of problems. For example, decision trees are easy to interpret, while neural networks excel at handling complex data like images and speech. Popular unsupervised learning algorithms include k-means clustering, hierarchical clustering, and principal component analysis. These methods help group data, reduce complexity, and uncover patterns. Each algorithm has unique strengths, making them suitable for different exploratory tasks. Imagine a self-driving car identifying stop signs and pedestrians. The car's vision system is trained on thousands of labeled images, learning to recognize objects and make safe decisions. This is a classic example of supervised learning in action, where labeled data guides the model's predictions. Consider a streaming service that recommends new music based on your listening habits. By analyzing patterns in user behavior, the system groups similar users and suggests songs you might like. This is unsupervised learning at work, finding structure in data without explicit labels. Preparing data for supervised learning involves collecting, cleaning, and labeling examples. This step is crucial because the model's performance depends on the quality of the data. Careful data preparation ensures that the model learns accurate and relevant patterns, leading to better predictions. For unsupervised learning, data preparation focuses on cleaning and organizing the data. Since there are no labels, the emphasis is on ensuring the data is accurate and consistent. This helps the model find meaningful patterns and reduces the risk of misleading results. Feature engineering is the process of selecting and transforming input variables to improve model performance. In supervised learning, this step can make a big difference, as the right features help the model learn more effectively. Techniques include scaling, encoding, and creating new features from existing data. In unsupervised learning, feature engineering helps the model find better patterns by highlighting important aspects of the data. This might involve normalizing values, reducing dimensionality, or extracting key characteristics. Good feature engineering can reveal hidden structures and improve the quality of the results. Overfitting occurs when a supervised learning model learns the training data too well, including noise and irrelevant details. This can hurt its performance on new data. Techniques like cross-validation and regularization help prevent overfitting, ensuring the model generalizes well to unseen examples. Unsupervised learning faces unique challenges, such as determining the right number of clusters or interpreting the results. Without labels, it's harder to know if the model's output is meaningful. Experimentation and domain knowledge are often needed to make the most of unsupervised techniques. Semi-supervised learning combines elements of both supervised and unsupervised learning. It uses a small amount of labeled data along with a large amount of unlabeled data. This approach can improve performance when labeled data is scarce, leveraging the strengths of both methods. Supervised learning is widely used in fields like healthcare, finance, and marketing. It powers applications such as credit scoring, disease prediction, and personalized recommendations. Its ability to make accurate predictions from labeled data makes it a cornerstone of modern machine learning. Unsupervised learning is essential for exploratory data analysis, market segmentation, and anomaly detection. It helps businesses understand customer behavior, detect fraud, and organize large datasets. Its flexibility makes it a valuable tool for discovering new insights in various industries. Supervised learning often requires significant human involvement, especially in labeling data and evaluating results. Experts are needed to ensure the labels are accurate and relevant. This human touch helps guide the model's learning and ensures it meets the desired objectives. In unsupervised learning, human involvement is more focused on interpreting results and deciding how to use the discovered patterns. Domain expertise is often needed to make sense of the output and apply it effectively. This collaborative approach helps turn raw insights into actionable strategies. Let's summarize the key differences between supervised and unsupervised learning in a simple table. Supervised learning uses labeled data and is best for prediction tasks, while unsupervised learning works with unlabeled data to find patterns. Each has unique strengths and is suited to different types of problems. Choosing between supervised and unsupervised learning depends on your goals and the data you have. If you need to predict specific outcomes and have labeled data, supervised learning is the way to go. If you want to explore data and find hidden patterns, unsupervised learning is your best bet. Future of machine learning will likely see more integration of supervised and unsupervised methods. Advances in semi-supervised and self-supervised learning are already making it easier to leverage both labeled and unlabeled data. As data grows in complexity, these hybrid approaches will become even more important. Ethics play a crucial role in both supervised and unsupervised learning. Ensuring data privacy, avoiding bias, and maintaining transparency are essential for building trustworthy models. As machine learning becomes more widespread, ethical considerations will remain at the forefront of research and application. To recap, supervised learning relies on labeled data to make predictions, while unsupervised learning finds patterns in unlabeled data. Each approach has its strengths, challenges, and ideal use cases. Understanding the differences helps you choose the right method for your data and goals. Thanks for joining this exploration of supervised and unsupervised learning. Now that you understand the key differences and applications, you're better equipped to tackle machine learning challenges. Keep exploring, experiment with different approaches, and stay curious as the field continues to evolve.